Wave interference is the interaction of two or more waves, or wave pulses. So let's visualize this using this simulation. So we'll send a pulse through this string, and another pulse. And because it's a fixed end, this pulse gets reflected and inverted when it reaches the boundary. And then these two pulses interact. So that's what happens when they're next to each other. And as they're traveling through each other, they're going to cancel each other out. So let's just keep this going. So this is when the pulses have overlapped. And then we continue the simulation. So basically when two or more wave pulses or waves interact with each other, they overlap and travel through each other. So they don't bounce off each other. So here we can see a wave pulse traveling at some wave speed v, and another wave pulse that may have been reflected from the boundary and travels in the opposite direction. And here we can see that when the two pulses are in the same phase and they interact with each other, the resulting amplitude can be obtained by adding the individual amplitudes of the pulses. So when these wave pulses are overlapping and they're in the same phase, if this is an amplitude of 1 unit and this is an amplitude of 1 unit, then the resulting amplitude will be 2 units. And similarly at the trough, we add -1 and -1, and that gives a displacement of -2. So this is called superposition, and in this case we have constructive interference, because the two wave pulses are in the same phase and they line up, so they constructively interfere to cause an increase in amplitude. Now in this case, we have destructive interference, because we can see the wave pulses are not in the same phase. So for example, if this wave pulse was traveling to the right, and this wave pulse was traveling to the left, and then they line up after a certain time, then because these wave pulses are out of phase, superimposing them together is going to cause them to cancel each other out. So that's what we call destructive interference. So for example here, we have -1 plus 1 gives 0, and 0 plus 0 is 0. So these pulses have effectively cancelled each other out. And as we saw in the simulation, these pulses travel through each other. So after they interfere, they proceed in the direction that they were traveling. And in this case over here, we can see the constructive interference of two waves, because these waves are in the same phase, and the peaks and the troughs line up together. So if the source of the wave in this case was moved to the right by 1 wavelength, or an integer multiple of the wavelength, then this peak will still line up with this peak, and this peak will line up with this peak. So you'll still get constructive interference. But if the source of the wave was shifted to the right by half the wavelength, then we can see that this trough will line up with this peak, this trough will line up with this peak, and so on, which can be seen on the right here, and you'd get destructive interference. So we can see that these two waves are basically cancelling each other out. So for example, if you had two speakers that emitted sound waves that were out of phase, and suppose the point where the sound was received is somewhere here, then you can see that these two waves are going to cancel each other out. And if this is done perfectly, then no sound can be heard at this point. And an example application is noise cancelling headphones. So really have a think about this. Beats arise from the superposition of two waves with a slightly different frequency. So for example, if we have one speaker emitting a wave at some frequency and another speaker emitting a wave with a lower frequency, then given these two waves are sometimes in phase and sometimes out of phase at different locations along the waves, this causes periodic amplitude changes in the resulting wave. So this is different to the cases we saw previously of constructive and destructive interference, where the amplitude of the resultant wave is uniform. Now we can see that the waves are in phase at a certain point, and they're completely out of phase at another point, and then they're in phase again, completely out of phase, and so on. So here we get constructive interference, followed by destructive, constructive, destructive, and so on. And this is a phenomenon called beats. And at a location where someone is listening, given that this wave is moving at a certain velocity, then a person would hear varying amplitudes. So you'd hear the high amplitude, and then you'd hear nothing, high amplitude, nothing, and so on. So this would sound like a wobble. Now the beat period is defined between these two locations, where the two waves are in phase. Now the number of cycles completed by the red wave after a particular time t is the time by the number of cycles per second, which is the frequency. And similarly for the green wave, the number of cycles completed after time t is the time t by the frequency of the second wave. And after one beat period has elapsed, we can see that the red wave completed one additional cycle compared to the green wave. So this is true from this point to this point, where you get constructive to constructive interference, and this cycle repeats itself. And now we can substitute for N1 and N2, so we get TF1 is TF2 plus 1, and then dividing through by time t, and subtracting F2 from both sides, we get 1 on t is equal to F1 minus F2. So therefore, given this relationship, t is the beat period, and therefore 1 on t is the beat frequency. And we take the absolute value in the case where F2 was greater than F1. So this tells us the beat frequency is the difference in frequencies of those two waves. Now tuning forks are devices that are commonly used to demonstrate beat frequencies. So for example, if you had two forks that are set to slightly different frequencies, and you tap them both at the same time, you'll hear a wobble. And an application of a tuning fork is to tune musical instruments. So for example, you'd set the frequency of the tuning fork to be some frequency and tap it, and then you'd pluck the string of the guitar, and that'll vibrate at some other frequency. And if you hear a wobble between these two frequencies, that's the beat phenomenon. So you tighten or loosen a string on the guitar, so the frequencies match and you no longer hear the wobble. Standing waves can result from the interference between two waves that are travelling in opposite directions and confined to a region in space. So basically they're formed based on wave interference and the boundary conditions of the region. And let's visualize this in a simulation. So if we oscillate this string back and forth, we have a wave travelling from left to right through the string, and that gets reflected downwards, and then the interference between these waves gradually create a standing wave. So in this case, we have a fixed boundary condition such that there's no displacement at both ends of the string. And if this were a sound medium, then if you consider these particles being initially at rest at 0, 1, 2, 3, 4 and 5, then considering this standing wave at this point in time, we see that at location 1, there's a negative displacement from equilibrium, so this sound particle would move to the left. And here we have a smaller displacement from equilibrium at position 2, so there's a smaller displacement to the left. And at position 3, we have a positive displacement from equilibrium, so the particle moves to the right. And a positive displacement that's larger at position 4. And at position 5, there's a node, so there's no displacement at this position. So this is the behavior of a sound wave, but a wave in a string is transverse, so the particles in a string move in a transverse direction, being a transverse wave. So in this case, we initiated our oscillation carefully to ensure we can create a standing wave with its wavelength being equal to the length of the string. So let's add 1.5 waves along the length and visualize what happens. So again, the wave propagates through the string and gets reflected upside down at a fixed boundary, and gradual interference between these two waves creates a standing wave. So in this case we have more nodes along the length. So there's no movement at the nodes at around this point and this point and at the ends of the string. And let's just do one more. So in this case we'll add 2 waves along the length, and we can see the gradual interference from right to left to create a standing wave. So we see that there's more nodes along the length where there's no displacement from the equilibrium position. So these are the different ways we can form a standing wave that has nodes at the ends of the string. So we call a node a point on the standing wave where the displacement is 0. So these are nodes. And a point on the standing wave where the amplitude is always a maximum is called an antinode. And the possible wavelengths to form a standing wave are determined by the size of the region and the boundary conditions of the region to which a standing wave is confined. So in this first case, the wavelength required to form this standing wave with nodes at the ends of the string to satisfy the fixed to fixed boundary condition is 2 times the length of the string. So as we can see, we have half a wavelength here, and if you continue drawing this sinusoidal wave, you get a full wavelength. And in this second case, we have 1 full wavelength along the length of the string to form this standing wave. So we have lambda 2 is equal to the length of the string. And in this third case, we can see that we have one full wavelength plus half a wavelength being equal to the length of the string. So 1 plus a half is 3 on 2 by lambda 3 is equal to the length of the string. So therefore in this case, the wavelength is 2/3 of the length of the string. And similarly for n equals 4, we have one wavelength plus two wavelengths along the length of the string. So we have 2 lambda 4 is equal to L. So the wavelength in this case required to form this standing wave that satisfies the fixed-to-fixed boundary conditions is half the length of the string. And I'll let you obtain the wavelengths for the rest of these cases. But now we'll come up with a general wavelength to form standing waves with fixed-to-fixed boundary conditions. So considering lambda 1, we can write lambda 2 being equal to lambda 1, which is 2L on 2. And lambda 3 is equal to 2L on 3, or lambda 1 on 3. And similarly, lambda 4 is L on 2, or 2L on 4. So if we take the fraction of lambda 1, we can write this as a harmonic sequence. So we have 1 lambda 1, 1/2, 1/3, 1/4, and so on. So you can see where the harmonic series comes from, if you've taken calculus. Now a standing wave, with the longest possible wavelength, being this first case here, is called the fundamental or first harmonic. And the standing wave with the second longest wavelength is the second harmonic. And the third longest wavelength is the third harmonic, and so on. So there's an infinite number of harmonics. And we can visualize the following general relationship with the first harmonic. And we're going to see that we can create standing waves with a node at one end and an antinode at the other, where in that case only odd harmonics can be established. And the common regions where standing waves can be formed include pipes with open and closed ends, as well as strings with fixed or loose ends, which are commonly found in musical instruments. Let's consider this tube that's open at one end and closed at the other. And if we disturb the particles at this end by blowing on a tube, for example, then we're going to cause the particles at this end to oscillate back and forth. And because the tube is closed at this end, the particles can't oscillate back and forth. Then we're going to have the maximum displacement of the particles at this end. So this will be an antinode. And at this end, there's no displacement, so it's a node. So for this to happen, we need to select the wavelengths that can produce a standing wave that satisfies these boundary conditions of the region. So in this first case, being the standing wave, n equals 1, so that's the fundamental or first harmonic, we get a maximum displacement of the particles that gradually drops off as we move from the antinode to the node. And now let's briefly observe this in a simulation. So again, we initiate the oscillation at the open end of the tube, and this propagates to the closed end. and this wave gets reflected, and the interference between these two waves gradually creates a standing wave. So in this case we have an antinode at the open end and a node at the closed end. So considering that these sound particles started at position 0, 1, 2, 3, 4 and 5, we can see the maximum displacement of the particle occurs at the antinode, and that displacement gets smaller and smaller down to 0 at the node. And here we can see the wavelength of the standing wave is going to be 4 times the length of the tube. If you can visualize extending this wave into a sinusoidal wave. So this is 1/4 of a sinusoidal wave. And now if we select our next wavelength required to form this standing wave with an antinode at one end and a node at the other, again we have our incident wave propagating. So we oscillated this a bit faster. Then that gets reflected, and a gradual interference forms a standing wave. So as we can see, again we have an antinode at this end and a node at the other. But this time we have 2 antinodes. And if we go to our next harmonic, again we can see the gradual interference between the incident and reflected waves. To create another standing wave. So this time we have nodes at position 5, 3 and 1, so there's no displacement. And we have antinodes at position 0, 2 and 4, where the maximum displacement occurs. So you can see that we have 1 sinusoidal wave plus 1/4 of a sinusoidal wave to form this standing wave. So for our standing wave here, with the longest possible wavelength, which has an antinode at this end and a node at the other, has 1/4 of the sinusoidal wave along the length of the tube. So therefore lambda 1, being the wavelength of this standing wave, is 4 times the length of the tube. Now for our second harmonic, if we follow this standing wave, we have from node to node being half a wavelength, and from this node to the antinode we have a 1/4 wavelength. So therefore we have 3/4 of a wavelength along the length of the tube. So therefore the wavelength of this standing wave is 4/3 of the length of the tube. Now for this third harmonic, if we follow this wave, we have 1 wavelength between these nodes plus 1/4 of a wavelength. So 1 plus 1/4 is 5/4. So 5/4 of a wavelength is equal to the length of the tube. So the wavelength of this standing wave is 4/5 of the length of the tube. And finally, from node to node, we have 1 wavelength plus 1/2 plus 1/4, or 1 3/4 wavelengths for this standing wave. So that would be 7/4 of a wavelength is equal to L. So therefore lambda 4 is 4L on 7. So therefore using the wavelength of the fundamental or first harmonic, we have lambda 2 is lambda 1 on 3, and lambda 3 being lambda 1 on 5, and lambda 4 is lambda 1 on 7, and so on. So we see that for a standing wave with a node at one end and an antinode at the other, we can only establish odd harmonics. Because to get a mathematical relationship between the length of the tube and the wavelength of each harmonic, being lambda 1 on n, then we need to make n an odd number. So we have n equals 3, n equals 5, and n equals 7. So therefore we can index the wavelengths of these harmonics as odd numbers. And then that gives us our relationship between our subsequent harmonics and our fundamental or first harmonic, which effectively depends on the length of the tube.